Hello. In this problem, the surface charge densities of three concentric spherical metal shells are given. We're asked to find the electric potential of each of these spheres, and also if the potential of shell A and then shell C are same, then what do you think is the relationship between the radii of the shells? Okay. So let's start by drawing the shells. Okay, so we have these shells A, B, and then C. The radius of the innermost shell is A, the middle one is B, the outermost one is C. Okay, so the surface charge densities are the innermost shell has plus sigma, the middle one has minus sigma, and the outer shell has again plus sigma. Okay, so if we write down the charges, let's say the charge on A will be surface charge density into surface area. Okay, so sigma into 4 pi A square, and charge on B is minus sigma into 4 pi B square, and charge on C is sigma into 4 pi C square. Okay, and so how do we calculate potential at a particular point? The potential at a particular point is generated by charge everywhere. Okay, so if I take a point just outside A, the charge on shell A will generate a potential at that point, and then so will charge on shell B and then shell C. Okay, so let us look at how to get the potentials at each of those shells. Okay, so here I have put a table to keep track of the potentials of each of the shells due to the charges on each of the shells. So let's start by looking at shell A. So at a point on shell A, charge on the shell will create an electric potential. So it will be the potential just outside the shell. So it will be 1 by 4 pi epsilon naught charge, so which is q a, which is sigma into 4 pi a square, then divided by a. Okay, now the potential, the charge on shell A will generate a potential at B and then C depending on the distance from the center of A. Okay, so this charge on A will generate, let's say at point B, the distance of a point on shell B from the center is B. So charge QA will generate a potential, so 1 by 4 pi epsilon naught. So charge QA is responsible, so sigma into 4 pi A square. But at B, we are supposed to use the distance B. And then similarly, for a point on C, the potential will be 1 by 4 pi epsilon naught sigma into 4 pi A square by C. Okay, now let us look at how charge on shell B is contributing to the potentials. Now let's look at shell B itself. Okay, so forget about A and C. So it would generate a potential 1 by 4 pi epsilon naught. Okay, so charge on B, which is minus sigma into 4 pi B square by B. Okay, now if you move outwards, okay, so to shell C, the same charge will generate a potential of 1 by 4 pi epsilon naught minus sigma, so charge is minus sigma into 4 pi b square divided by distance of point C, of any point on shell C from the center, common center, which is C. Okay, now if you go to any point inside shell B, the charge on shell B will generate the same potential which is there outside it. Okay, so anywhere inside. So that means the shell of A due to charge on B will still be this cell, the middle cell, the potential in the middle shell, so which is 1 by 4 pi epsilon naught minus sigma into 4 pi B square by B. Okay. Now let us look at how charge on shell C is generating potential. Now let's think about a point outside shell C. Okay. So the potential outside shell C will be 1 by 4 pi epsilon naught. Okay, charge on the shell, which is sigma 4 pi C square divided by C. Now if you get inside shell C at any point, okay, so be it at a point shell B or shell A, the same potential will be there as that of the potential at a point just outside shell C. So everywhere inside the potential will be same. So 1 by 4 pi epsilon naught sigma 4 pi C square, that is the charge, by C. So even on top of shell A you will have the same potential. So sigma 4 pi C square by C. So now we are done. So if I add the potential values of each row, I will get the potential of each shell. So let's do that. So from here, what do we get? The potential of A. Okay, I think everywhere you can ignore 4 pi. Okay, and then I can take sigma and then epsilon naught common. So we get sigma by epsilon naught. Okay, from the first cell I have A, second cell I have minus B, and the third cell I have C. So similarly, what is the potential of B? Again, sigma by epsilon naught common. And then what do I get from the first cell? I have A square by B, and then I have B square by B from the second cell. So we can write A square minus B square by B plus C. Now, what is the potential of shell C? Again, sigma by epsilon naught is common, and I have A square by C, B square by C. So I have A square minus B square by C plus C. Okay, so these are the potentials of each of the shells. Now, looking at the part B, question part B, the potential of A and C are equal. Okay, so if VA equal to VC, okay, so now take a look at these values. Okay, so if these two are equal, and then C and C, I think we can forget about that. So what can we say here? Okay, so for VA is equal to VC, I can say that it implies A minus B is equal to A square minus B square by C. I think let us do this in a different board. Okay, so here we have the potential of shells A and C are equal. So if you compare, I think A minus B is equal to A square minus B square by C. Okay, so the right hand side I can write it as A minus B into A plus B by C. So here if I take C to the left hand side, I have A minus B. Maybe I'll borrow this to the left hand side. This is just algebra equal to 0. So that means A minus B and C minus A minus B is 0. So here either A minus B, which is A equal to B, or C minus A minus B equal to 0, which is C equal to A plus B. But we know that A is not equal to B, right? So this is not possible. So that means the relation is C should be A plus B, so that A and C have the same electric potentials.